So hello everyone, today we'll be solving this problem, negative prefixes, which I've already posted on Discord. So you're given an array consisting of n integers. Each position I of the array is either locked or unlocked. You can take the values on the unlocked position and rearrange them in any order and place them back into the unlocked positions. You are not allowed to remove any values, add the new ones, or rearrange the values on the locked positions. You're allowed to leave the values in the same order as they were. Okay, so you can either remove or and rearrange these unlocked ones, or you can leave them as it is, but you cannot add new elements or remove new elements. Fine, you can just rearrange the unlocked ones. I hope that's pretty clear. For example, let a equal to, okay, so and so. What I need to do, let p be a sequence of prefix sums of the array after the rearrangement. So p1 equal to a1, p2 equal to a1 plus a2, p3 equal to a1 plus a2 plus a3, pn equal to a1 plus a2 plus so on till an. That seems fine. It's the normal prefix sum. And let k be the maximum j such that pj is less than 0. If there are no such j such that pj is less than 0, then k equal to 0. Your goal is to rearrange the values in such a way that k is minimum possible. Okay, k is minimum possible. Output the array after rearrangement. Fine. So I hope the problem statement is pretty clear. You can rearrange the unlocked items and you need to like maximize the prefix sum, isn't it? You need to maximize the prefix sum. So somehow this gives you some sort of greedy vibes, right? Because you know something that what do you know? If you maximize p of 1, if you maximize, let's say p of 1, let's say you maximize p of 1, okay, that means basically a of 1 is maximum, a of 1 is maximum. If a of 1 is maximum, can I say that a of 1 would be in every prefix? A of 1 would be in every prefix. A of 1 would be in every prefix. A1, A2, so on till an. A of 1, as you can see, A of 1 is in every prefix. So for n prefixes, there would be A of 1. Okay. For n prefixes, there's n times A of 1, n minus times A of 2, n minus 2 times A of 3. That means if I'm considering it to be the maximum, if I want to maximize this particular prefix sum, then is that very clear that I need to maximize A of 1? Then since the next highest appearing element, highest contributing element in this is A of 2, and the third highest contributing element is A of 3, that means A of 1 should be the first maximum, A of 2 should be the second maximum, A of 3 should be the third maximum. Isn't it? Isn't it? All right. This is what you'll think. But today we'll be learning a technique known as exchange arguments. We'll be learning about a technique known as exchange arguments by which you can prove that whatever you're thinking is right. Because sometimes while solving greedy problems, your mind may say something which might be wrong. You may never know. So that's the problem. So we use something known as exchange arguments. So what are these exchange arguments? The basic exchange argument is nothing but it's a proof by swapping. Exchange argument is a proof by swapping. So what does this proof by swapping means? What does this proof by swapping means? Let's say I need to only rearrange, and we use this exchange arguments only when we have to rearrange in an optimal way. Whenever the thing is rearranged and you'll have some optimal way, you'll be using this exchange arguments, and we'll be understanding the true beauty of exchange arguments in upcoming classes, like upcoming sessions. But for now, I'll tell you what are basics of exchange arguments. So I wanna arrange u1, u2, u3, u4, so on till ui, uj, so on till un, such that it gives me a maximum prefix sum, if you have figured out till here, actually this logic is right. I'm just proving so that I can show you that every time you may not be able to figure out this trivial logic because all the problems won't be this simple. So basically what am I trying to say? Sometimes greedy problems go trickier. In that case, how do you actually prove what you're thinking is right or wrong? So let's say you have this particular array, and now if you calculate the prefix sum for this, if you calculate the prefix sum for this, it would be like u1, u1 plus u2, u1 plus u2 plus u3, u1 plus u2 plus u3 plus u4. And if you, what is proved by swapping? You basically take two values, ui and uj, and just swap them, and just swap them. Okay, and just swap them. If whatever you're thinking, this particular thing is an optimal solution, if this is optimal, if this is the optimal solution, all right, this u1, u2, u3, u4, ui, uj, so until un, if this particular arrangement gives you the optimal solution, what does it mean? All other solutions would be, all other solutions would be less than or equal to this particular thing. That means this would be greater than or equal to any other solution. If this is really the optimal solution, if this is really leading to the maximum, if this is really leading to the maximum, this particular solution would be greater than or equal to any other solution. So even if you calculate the prefix sum till here, u1, u2, u3, u4, u5, and so on till uj, ui, and un, if you calculate the prefix sum till here, and if you calculate the prefix sum till here, both of them would cancel out. Okay, and all of these things would cancel out. Okay, and you'll be left with, all these things would cancel out, and you'll be left with ui, uj, prefix sum of ui, uj, let's call it prefix sum of ui, uj, is greater than or equal to prefix sum of uj, ui, isn't it? Isn't it? So what do we get? Prefix sum of ui, uj is basically ui plus ui plus uj. Ui is the prefix sum of this particular thing, and ui plus uj is the prefix sum of ui, uj. That means, and uj is the prefix sum of this thing, and ui plus uj is the prefix sum of this thing. And we are considering uh, I to be, like, if this is the sorted order, if this is sorted in descending order, okay, if this particular thing is sorted in descending order, or else let's say ascending order. To contradict ourselves, let's say this thing is sorted in ascending order. Let's say it's sorted in ascending order. That means I should be less than j, isn't it? I should be less than j, and ui should be less than uj. If this is sorted in ascending order, ui should be less than uj. That means let's cancel out these two. Ui, you get ui is greater than or equal to uj, which contradicts this particular statement. When I is less than j, we had the statement ui is less than uj, which meant ascending order, all right. But you got the statement to be ui is greater than or equal to uj, that means descending order. That means initially whatever we thought, we are able to prove it, that why sorting in descending order is actually right for this problem. We are able to prove why sorting in descending order is actually right in this problem. However, this is a very basic problem. You can directly come up with the logic, but in complex greedy problems, many times these kind of logics are non-trivial. We'll be seeing one such problem. Okay, so if you don't engineer it properly, it would turn into a very complex problem. All right, so let's code this up first. Okay, from the exchange arguments, we have derived that we need to sort in descending order. We need to sort unlocked, what were they, unlocked components, or what was it? whatever. We need to sort unlocked in descending order. So first thing, what's the input statement? It was n as far as I remember, and then it was supposed to be, okay, first line is n, second line is a1, a2, a3, fine. And so we'll be writing vector int a of size n, and the third line was supposed to be l of I is 1. That means the position is locked, otherwise the position is unlocked. Okay, so we'll be taking this vector int l of n, and to actually sort the unlocked, we need to store them separately, right? We need to store them separately. So let's store them separately in a different vector, and so int I equal to 0, c in l of I. Okay, so let's write some bool function. Bool is unlocked. So this would take int n, and it will basically return n equal to 0. Okay, so we'll write is unlocked of, okay, L of I. If it's uh, if it's an unlocked element, then we can do it. We can do push it into unlocked. We can push back this A of I. All right. Now, from exchange arguments, we derived that, or by logic, we derived that unlock should be sorted in descending order. So let's sort it in descending order. You can use the by default STL comparator, or else you can write your own also. Usually while solving these exchange argument problems, we write our own comparators by deriving the logic. All right. So let's take an inserter variable to basically insert the right things, insert the right unlocked stuff from the unlocked array. Okay. So let's take for int I equal to 0, I less than n, I plus plus. If L of I is equal to 0, then you can simply do cout unlocked of inserter. You can call it inserter or anything you wish to. Sorry, not indel, it's space. Otherwise, you would see out A of I. Here also space. And now let's do cout indel. That should be fine, isn't it? We just need to sort the unlocked in descending order. Why is it taking so much time to run? So we received nothing because, okay, we didn't put the test cases. That was pretty bad. So first line contains test cases, and then yeah. So why is it printing this way? Expected output is this. Nothing is logged here. So yeah, it should print it this way. Otherwise, we have 2, 3, -1, 4. Okay, we added the indel statement here. This should be here. Fine. So let's try this out. Logically, we are right. And it's accepted. So yeah. Now let's have a brief discussion on exchange arguments once. Okay, so let me tell you when do we actually use them. So let me take another problem, minimum scalar product. Not this one. Okay, so basically, let me take a random question. So this was asked in the very recent Amazon one. Not the very recent one, I guess actually. It's an actual Google Code Jam question. It's a Google Code Jam question. It's a Google Code Jam. Don't remember which year, honestly. And then one of my friend told it was asked in his Amazon OI also. So let's see this problem. So the problem basically says you'll be given n-dimensional vector. You'll be given a couple of n-dimensional vectors, two n-dimensional vectors, and let's say the two vectors are a1, a2, so until an. These are like the coefficients of vectors, like a1 I cap, a2 j cap, and etc. And b bar is b1 I cap, b2 j cap, so on till bn. And I need to minimize their dot product. This is what I have to do by rearranging. Okay, you need to minimize the dot product by rearranging. And the first weird thought that comes into your mind, because your mind tricks you obviously while doing greedy problems, is that okay, when I multiply two small numbers, I get a small number. When I multiply two bigger numbers, I get a bigger number. So dot product is all about multiplication and addition, right? Dot product is all about multiplication and addition, right? So if I want to minimize it, I would multiply minimum into minimum. And it would magically pass all the test cases. This is what an average person thinks. But there's a catch. If you observe carefully, first observation is that forget about taking a test case and dry running it and doing all that stuff. Those things are not really possible in a contest because in that stress you cannot actually take some numbers and solve the whole thing. So directly, whenever it's something related to rearrangement and it's something related to optimality, so it's obviously a question of dynamic programming or greedy, isn't it? It's about rearranging and it's about optimality. It would be a question of dynamic programming or greedy. So directly before jumping to the dynamic programming approach, greedy one is always better, isn't it? It's easy to code, it's more efficient, and you need not handle multiple recurrence relations and stuff, isn't it? So greedy is always better to think of. And how to check if a greedy solution actually would work or not? How to check if a greedy solution would actually work or not? First thing, derive the greedy solution. How would you derive the greedy solution? The question is about rearranging. That means you need to apply something known as exchange arguments. You need to apply something known as exchange arguments. By the way, this thing is wrong. This intuition is completely wrong. So let me tell you. If I want to minimize the dot product, I want to minimize the dot product. That means A1, A2, so on till AI, AJ, so on till AN, and B1, B2, so on till BI, BJ, so on till Bn. Let's say this is the case. And tell me one thing, I got only two choices. I'm minimizing and maximizing something. So by trial and error, I can say that one thing would be ascending sorted and one thing must be ascending sorted. This is one possibility. Or else one thing must be descending sorted and one thing must be ascending sorted. These are the only two possibilities, right? You might be like, wait, there's also another possibility, which is ascending sorted here and descending sorted here. I would say no, because what are you doing? You're basically applying the reverse loop. That doesn't make any sense. You're basically applying the reverse loop. At the end, you're computing again the same thing. So either you sort in opposite way or either you sort in the same way. So let's fix one thing. Let's take B to be ascending sorted always. That means write it down. BI is less than BJ and less than or equal to BJ, and I is less than J. BI is less than or equal to BJ and I is less than J. This is the condition for ascending sorted, isn't it? This is the condition for ascending sorted. Now you have two options. Either you can check your this minimum into minimum approach is correct or not, isn't it? Either you can check your minimum into minimum approach is correct or not, or else you can check for the maximum, basically the opposite sorted condition. So if I check this minimum into minimum condition, because it's ideal for me to check it, I have thought that this would give me the right answer. Maybe it's failing a test case. Maybe you realized earlier that it's not working. So you can always check the right logic. If you know something, if you just know a wrong solution, you can check it out. So I know a wrong solution, or possibly a right solution. I don't know. Let's say I just know a solution. It could be right or wrong, minimum into minimum. So let's say I have sorted this thing in ascending order, to get A's first minimum and B's first minimum, A's second minimum and B's second minimum, A's ith minimum and B's ith minimum. So can I say that if this is the optimal solution, basically A1 and A2 would cancel out in the inequalities. At the end, you have AI, AJ, BI, BJ in the array. This particular thing would always be less than or equal to AJ, AI, would always be less than or equal to AJ, AI and BJ, BI. Isn't it? This is what you're saying. You're saying that your solution minimum into minimum thing is optimal. Minimum into minimum would give you the minimum. This is your greedy logic that you have figured out due to your dumb brain. And you are trusting this logic to be true. That means this is optimal. And any other solution would not give you the minimum. That means this is any other solution. It would always be greater than your optimal solution, which you are assuming to be optimal. So now if I calculate dot product for this AIBI plus AJBJ less than or equal to AJBI, this is I by the way, AJBI and AIBJ. This is what I'm saying. So if I try to solve this particular equation, AIBI minus AJBI, I'll take this separately, and the BJ terms, right, plus AJBJ minus AIBJ. This is what I'll get. I'll get this as less than or equal to 0, isn't it? So if I take BI common from this, AI minus AJ, plus if I take BJ common from this, I get AJ minus AI less than or equal to 0. Okay, this simply means AI minus AJ multiplied by, okay, I'll make this a negative. I'll bring this negative out. That means this would become minus BJ into AI minus AJ. So AI minus AJ I would get as common, and BI minus BJ. This is what I'll get, right? And tell me one thing, if I'm doing bi minus bj, where let's say this bi minus bj, what did we derive here at the starting? Not derived, but we sorted this thing in ascending order, which means bi is less than or equal to bj. That means if this is less than or equal to 0, this particular thing would be negative, isn't it? This particular thing would be negative. Now coming to ai minus aj, if this particular thing is negative, to get the whole expression negative, ai minus aj should be positive, isn't it? Ai minus aj should be positive. That means ai is greater than aj. That means ai is greater than aj. That means that means ai is greater than aj. What does this mean? That means there exists this sequence a1, a2, a3, so on. And if ai is greater than aj, that means this whole thing is descending sorted. That's what we derived. That means to get the optimal answer, to get the minimum dot product, we derived that a vector should be sorted in descending order, b vector should be sorted in ascending order. This is what we have derived. Is that clear? So if I try to write code for this, okay, not to waste time, let me take this template. So basically what I would do, I would take int n, one vector would be vector int a of size n, and one would be vector int b of size n, and I would take these vectors. In my template, I can directly do c in a and c in b. So that's a great thing about my template. And I should sort b in ascending order. And I should sort a in, sorry, a dot begin, a dot end in descending order, right? Descending order. Fine. And my minimum dot product would be int answer equal to 0. Minimum dot product would be for int I equal to 0, I less than n I plus plus, answer plus equal to ai multiplied by bi. Perfect. This is the exact logic. So I hope the session was clear. Now I believe no one would get stuck in deriving these kind of greedy solutions and contradicting your answers before actually submitting them. Fine. So this was the session for today. Thank you, everyone.